Hello everyone, good evening. Welcome to this live interaction session of week 4. So we'll start in a couple of minutes. So let's start. Um, right. So we were talking about filters in the last session. So I have found this link where you can see how different types of filters work. So this is a digital image. So you can see um, these DN numbers over here. I hope you are able to see this. So here the brighter pixels, they correspond to higher DN values. So this is an 8-bit image. So these brighter pixels, they are corresponding to higher DN values like 245, 255, 251, and so on. And here the darker pixels, they are corresponding to smaller DN values. So this is how a digital image would look in form of DN numbers. Now here we'll see how applying each filter would transform that image. So here you can select the filter that you wish to apply. So let's see identity filter. So we talked about this filter in the last session, right? So identity filter would be 000, 010, 000 again. So here if we see, yeah, identity filter would result in the same image itself. Next, we can check the blur filter. So here, the central pixel is given more weightage, and the uh, adjacent pixels and the corner pixels are given respectively lower weightage. So here, let's see in this figure. So for the central pixel, this is how the transformed image would look like. So we can move our filter in any part of the image, and we can check how the transformed pixel would look like, right? So here, say this is the darker pixel, which was corresponding to 53, but then after applying the filter, its value became 100, and the darker portion, it became slightly lighter. So here it would try to this filter would result in smoothening of the original image. Now next we can check the sharpening filter. So here the central pixel has the value of 5, and the side and top bottom pixels, they have -1. And after the application of this filter, we can see that the image is becoming more sharp over here. So the differences in intensities which were there in the previous image, now those differences have they have become more prominent. So uh, suppose uh, here, yeah, let's take the same pixel. So first it was 53 and it was slightly darker than its surrounding, and now after applying the filter, the value of this pixel has become minus 164, which is much, I mean, so the difference between its adjacent pixel has become more sharp. I mean, the difference is higher. That is why the image looks sharper. So I will provide the link to this site, and you guys can visit this and uh, try to check this check the transformation for different images, different filters. So you can try all the different filters like bottom sobel. It will create an output image like this, or uh, outline, it will create like this. So we haven't studied all these filters, but you can see how the uh, filter matrix is, and then you can check the output. So I'll give this link. I think you should try this uh, on your own, so that you'll get a better idea of how filtering changes transforms the images. So let's go and solve a few problems based on this. Right. So in the last class, we talked that spatial filters can be of two types. uh, Smoothing and sharpening. In smoothing, we saw average and linear. So, and then there was second one, which was order statistics, non-linear, and there was sharpening. So we hadn't seen order statistics and sharpening. So let's solve this problem on order statistics filter. So I'll give you a couple of minutes and you can try to solve this problem. So median filter was explained in the lecture, so you can try this problem. So median filter is a type of order statistics nonlinear filter. So if this is my central pixel, then we will examine the neighborhood of this pixel, and then we'll find the median value of all the 9 pixels, and the central value will be replaced with the median. So this median filter can be useful in removing impulse noise. So we'll see an example of that. So what you can do is for each pixel, consider the neighboring 3 cross 3 matrix around it, and then try to find the median value of each 3 cross 3 matrix for the 3 highlighted pixels. Did anyone get an answer? Okay, so let's see this. So for the first 91. Okay, we'll see. Anyone else? Okay. So let's see for 255. So to calculate median of a population, what we do is we arrange all the numbers in the ascending order and take the central value, which is the median of that population. So here we have 9 values. So first we'll arrange them in ascending order. So for 255, we have right. So this is the ascending order, and since these are 9 pixels, fifth pixel would be the median one. So this.
1 second. See, you have taken the 3 by 3 matrix, right? Any specific reason we have chosen only those cells? I mean those pixels?
Yeah. So in this 5 cross 5 image, we can only take 3 by 3 matrix.
Yeah, but any 3 by 3, right?
It should be the neighboring for that 3 by 3. So we are trying to apply the median filter on three shaded pixels. So we want to apply it on 255, 70, and 0. Right.
Yeah.
So first I am trying to calculate for 255. So for 255, I will only take the pixels which are neighboring 255.
Okay, so independently, 3 pixels we have to calculate.
Yeah. For 3 pixels, we'll calculate it independently. So, so if you look at this 5 cross 5 image, this 255 and 0, it looks like an impulse error because it is very high and this is very low with respect to its neighbors. So it could be because of an error. So to remove this error, we apply this median filter. So before this value, the central value was unusually high, like 255. But now after applying the median filter, the value of this pixel would become 30. Now for 70, again we will consider now this neighboring matrix here. So again, we have to arrange these 9 values in ascending order. So we have 0, and 255. So here the value of this pixel would be 80, and for 0, this would be the neighboring matrix. So we will arrange it in ascending order. So we have again 0. So this is my value. So now 0 is transformed to 80, which is now closer to its surrounding pixel. So the impulse error, so the error which was there because of these unusually higher or lower values, it will be removed by applying the median filter. So I hope this was clear. So here is an example of how the median filter would transform the image. So here, the first image, it shows error.
Will you please show previous slide again? Okay.
Yeah. So these small dots in this
So
image.
this new image filter would have the average of three medians.
No. So this these older values, they will be replaced by medians. It wouldn't be average. So my new image, it will look like this. So we calculated it for 3 pixels. No, so we will replace 3 pixels.
Okay. So instead of 255, we'll add it as 30, and then 70
Yes.
it's 80, and then 0 100.
Yes. Okay. Okay. So this is the original image, which contains this salt and pepper noise, where the image looks very grainy because of the presence of some high intensity or low intensity pixels. Now here, this figure B. This is the result of applying a 3x3 standard averaging filter. So we are here after applying the averaging filter. Still, the salt and the error which is there, the graininess of the image, it is still there. So applying averaging filter would not be useful in this case. But then after applying median filter, the image looks clear of all the error which was there in this figure. So this is how the product of applying median filter would look like. Okay, so we saw smoothing filter, where we saw average linear filters and order statistics nonlinear filters. Now we'll move to sharpening filter. So in sharpening filters, after we apply the filter, so what we saw before starting the lecture, that sharpening filters would make the intensity variations in the image more prominent. So let's see how derivatives. So to make the image more sharp, to make it more smooth, we apply averaging filter. So to make it more sharp, we will have to calculate the derivatives, because derivatives would measure the intensity of the change. So let's look at this image and try to understand it better. So this is the sorry. Yeah, this is the scan line here, and these are the original DN numbers in this scan line. So here we see this is 666, and then it's changing, and this is how the variation looks. So here the intensity transition is gradual, and here it is slightly steep. So let's see uh, the how calculating the derivatives would uh, show these intensity transitions. So for the first derivative, we check what is the change between what is the intensity change between adjacent pixels. So here this 6 to 6 is 0, then here again 0, then 6 to 5 is -1, then 5 to 4 is -1 again, and so on. So this is the first derivative, and then we calculate the second derivative, which is here. So it will be how the change is occurring in the first derivative. So here from 0 to 0, it's 0, then here it's -1, then -1 to -1 is 0 again, and so on. So here the change is from 5 to 0, and in the second derivative it would be 5 to -5. So when we are showing the second derivative, in that case, so these white boxes are the second derivative. So here the change, the intensity change would appear very steep.
Actually, this letter and letter size, that number size is very small. It's not properly understood. Can you zoom it? This image, can you zoom little bit? Yes, yes. Now, if you explain, at least I can understand.
Okay, so here so this is an example of a Laplacian filter which uses the second order derivative to sharpen the image. So we are looking at how this second order derivative will bring change in the intensity levels compared to the original image. So here this is your this is the data from the original image, the scan line, right? So these are the DN values. So here we calculate the first derivative based on how the DN values are changing, and then we calculate the second derivative based on how the first derivative is changing. So here, so these were the intensity transitions. These were the intensity transitions in the original image. So here the pixel intensity is 6, it's gradually decreasing, and here it's increasing from 1 to 6. So there is a sharp increase over here. Now after we calculate the second derivative, we see that here these white boxes, they show the second derivative. So here the intensity change is not as much, but here where there was a steep rise, there the second derivative shows a very steep change. So if this pixel is 5, so this pixel, the pixel next to it has the value -5. So the change over here is more sharp. So it will make the image appear more sharper. So if we want to look at it mathematically, so Laplace first derivative.
One clarification. See, in the first derivative, right? I think you said something Wrong. Like, see, in the scan line, right? From begin value 6 to 6, it is 0. That I understand. And then again 6 to 6, 0. And the third, right? Third to fourth difference is 0 again, right? It again 6
Yeah.
and 6.
So I think they have not considered this pixel while calculating the first derivative. So
Yeah, but still,
this.
to get the first derivative of fourth dn value, we have to consider difference between third dn and fourth dn, right?
Right.
So it should be 0, but we are getting -1 there,
So this is the difference between these two, 2 and 3. This is 0 here.
right?
Next, you have 6 to 6. This is 0 again. Then this is 6 to 5. So,
Okay, okay. You mean they have started calculating from dn value 2, second dn value?
yeah, that's what I meant. So
Any
this,
reason?
they are
Any
not.
reason?
Okay, I do not know. I took this image from a online site. So I just wanted this to show this
Okay, okay.
for the sake of
Because
representation.
even for the first derivative of second dn value, right? We have to consider the first dn value because they have given it as 0 there.
Uh, which one are you talking about? So
if
this,
if we
this
if we suppose first dn value is not considered, then we cannot calculate the first derivative of second dn value, right?
okay, right. So yeah, we can write it here. It's fine. I mean that is so it's there on. It was there in the book. So yeah, you're right. I
No,
think.
that's okay, that I understood, but I'm just trying to understand myself how to calculate the derivatives.
Yeah. So you understand the concept, right? This
Right,
is
right.
pixel shifting. I mean, they
And
did
the
not
second derivative should be calculated based on the first derivative, right?
based on
Difference.
the first derivative. Yes.
Okay, okay, thank you.
Yeah. So you're right. So if we have 0 0 in the second derivative, then there should be 3 zeros in the first derivative.
Yeah.
Yeah. So uh, for a pixel, so suppose this is an image. So each pixel would have so each pixel would be represented as a function of x and y. So to calculate first derivative along the x direction, uh, we'll have to write uh, f of x plus 1 comma y minus f of x comma y. Yeah. So the expression for second derivative would be uh, and similarly we can write for second derivative along the y direction. So the Laplacian filter, it uses second order derivative that we saw. So Laplacian filter is given as so we'll add 1 and 2. So we get f of so I hope this is clear.
Here, the first line, right? Df by dx is equal to f of x plus 1y minus f of xy. Is this the first derivative?
Yeah, this is the first derivative along x direction. So
Right.
yeah, so this is my central pixel. So this will be my f of x comma y. So this will be f of x plus 1 comma y. So it will calculate a derivative along x direction. And then this pixel would be f of x comma y plus 1.
Y plus 1.
Yeah. Then this pixel would be f of x minus 1 comma y. And this pixel would be f of x comma y minus 1. So if we look at this image, so this gives us the transfer Laplacian filter as 0 minus 1 0 minus 1 4 minus 1 0 minus 1 0. So this expression is like applying this filter on my pixel f of x comma y. Is this clear?
Yeah, I think we need to uh, like keep idea of this filter, just the matrix filter for the Laplacian. 0 minus 1 0 minus 1 4 minus 1 0 minus 1 0. For the problems to apply, right? We need to by heart this.
Yeah, so how this filter came is clear, right?
Right.
Okay. So yeah, this is one type of Laplacian filter. So if we are considering the corner images also, so if we are considering f of x minus 1, y minus 1, f of x plus 1, y plus 1, and so on. So in that case, there is another filter which is minus 1, minus 1, minus 1. Yeah. So I do not know about the derivation of this, but you can go and check. So yeah. So these are different types of Laplacian filters. So let's solve a problem related to this. So you can try this problem for a while, and then we'll solve it.
Is this multiplication or addition?
So it would be pixel to pixel. So 156 would be multiplied with 0, 158
Okay.
would be multiplied with -1. Then we add everything. So it would be 158 into -1 plus. So I was getting around -40.
Acha, will you please show previous slide, previous one?
Okay, so let's move to principal component analysis. So principal component analysis is mainly used to reduce the dimensionality in the data.
Actually, is the answer after multiplying -60. Sorry, -40. So we should reduce -14 from each pixel. Is it
Yeah, so from the central pixel we will reduce it.
only central pixel?
So we can apply that one for any other. Just show me previous one. For 154, we have to do like this. If it is any other number, suppose 156 or some other number.
Yeah, so then you will apply the same filter on the neighborhood of 156.
Okay, okay.
Um, is someone's mic on? Thank you. Okay. So yeah, principal component analysis is used to reduce the dimensionality in the data. So I'll explain what it is. And it is used to transform the data Yeah, so it is used to transform data into correlated variables, which represent most of the data. So, for example, in case of remote sensing images, what happens is that if we are talking about Landsat 8, then Landsat 8 has 11 bands, some 11 to 12 bands, I think. Yeah, and then all these bands, they span uh, different intervals in the electromagnetic spectrum. Now, for many of these bands, what happens is that the reflectance of the materials, it is more or less the same. So, for example, we looked at these images in the second interaction session also. So this was band 2 and this was band 3. So here the reflectance characteristics of water and vegetation, they are almost similar. So these two images also, this is band 2, this is band 3. So these two images, they almost look similar only. So they are not giving very distinct information. Whereas if we compare it with, this is band 5, which is in the near infrared. So it's somewhere here. So band 5 gives us slightly distinct information than the rest of the band. So there might be more bands spanning this spectrum where the information revealed is more or less similar. So when we are using this remote sensing information, we do not need uh, the same redundant information again and again. So what principal component analysis does is it reduces the, so if we are talking about Landsat 8, it reduces the number of bands from 11 to any smaller number less than 11. So it could be any desired number that we want. So it reduces it into smaller number of components, which shows which contain almost the same information which we were getting from these bands. And like how previously band 2 and band 3, they are correlated, right? So they are showing almost same information. But in after calculating the principal components, the bands in principal components, they would not be correlated with each other as the previous ones. So we'll look at few more examples. We'll talk about it, and then we'll solve some numericals based on this, so it will be more clear. Yeah. So this is an image which has 4 different sets of bands. So it has so this is band 1, band 2, band 3, and band 4. And these are the images which are showing the histogram distribution of DN values of all the pixels which are there in this band. So the coloring scheme used over here is a little different. So for band 1, we see that the histogram is centered around here, like 75 to 80. In band 2, it's somewhere centered around 50, but then both band 1 and band 2, they're spanning similar area and their shape is also similar. Then band 3 is slightly towards higher values, and band 4 is centered around 100 to 110. So here we see that band 1, band 2, and to some extent band 3, they are almost their distribution is almost same, and the images also appear same, and they are not giving any useful information. So
Yeah, sorry to interrupt. Small correct. See, when we say band 1, band 2, band 3, right? It always remains green, blue, green, red. Is it something like that we need to think? Or it differs when a true
uh,
composite in again
so for now, just think in terms of the distribution of histogram. So this is, I'm just giving an example. So this is a satellite image. So based on which satellite it's taken from, the blue, green, red would differ. So here I'm not sure what exactly are these bands. So we do not need to think in terms of that here. Here just see the distribution of the histograms.
But basically, based on the satellite configuration, the band changes.
Yeah, I mean, the interval would be given for each band, the wavelength interval in which to which the band is sensitive.
Uh,
So, yeah, exactly what principal component analysis does is, so after the transformation, here we see that this is one peak where the data is on the centered around 40, and this data represents all the darker pixels. And then here between 200 to 250, we see that there is a very small area which is spanning this range. So these are all the brighter pixel values. So here, after this transformation, the distinction between all the river channels and the surrounding vegetation is more clear. So this image kind of brings out more information compared to all the other images combined. So this image has the highest variance. And similarly, this is the second image. So here also we can see the distribution. I mean, distribution being split in two areas. So the darker pixels, they are representing the vegetation, and then the brighter pixels, they are so they're water pixels and surrounding. Okay, so we'll see that how we are reducing the dimensionality of the data. So suppose yeah, so this is band 1, band 2, band 3, band 4, and so on. And here are my individual pixels. So for each image, I'll have a set of pixels. So this would be, so here I would represent my each pixel, P3, P4, P5, and so on. So, yeah. So for each pixel, I will have a value in all the 4 bands. So let's take a couple of values. So right. So here we see that this band 2, the value is remaining almost similar in all the pixels. So it's not giving any extra information. So it is possible to remove this redundancy using the principal component transformation. So this P1, which is currently 4 dimensional, we want to change it to 3 dimensions. So for all the pixels, we would change. So we can make this into 3 or 2 or 1, depending on how many principal components we want. So how this transformation will go is, so if this is my x1, x2, x3, x4, and in the result I want only 3 bands. So this would be my transform data. Right. So the dimensions of this matrix are 3 cross 1 and this is 4 cross 1. So if I want a 3 cross 1 in the output, this should be 3 cross 4. So we will multiply the original number of bands by a transformation matrix to get the matrix in to get the principal component transformation output. So we'll see the process entirely. So here suppose, yeah. Right, so my y1 would be a11 x1 plus a12, and similarly we'll have y2 and y3. So this is my transform data. Okay, so before we go into the calculation of um, the eigenvalues and eigenvectors, we'll just quickly look at all the mathematical concepts that we would need. So it's very basic concepts, but for those who are from a different background, we'll just go over it quickly. So we have mean. So if my population is x1, x2, x3 up to xn, then my mean mu would be given as 1 by n summation r is equal to 1 to n. Then we have covariance. So covariance measures how two variables change together. So if this is the data set, then covariance of xy would be given by 1 by n. And here covariance matrix. So if I have a k dimensional data set, x1, x2 up to xk, then its covariance matrix would be given as this. And this can also be written as where C is my matrix containing these um, these variables. So we'll try to visualize how we are going to do this transformation. So suppose this is my band 1, this is band 2, and we are plotting the DN values. So if band 1 and band 2 are correlated, then their distribution would sort of look like this. And this is the mean of band 1, and say this is the mean of band 2. So when we do this coordinate transformation, what we do is we bring the reference frame to the center of this dataset at the means of band 1 and band 2, and then we rotate the coordinate frame to bring the major axis along the direction of maximum variance. So this would be the direction of first principal component, and this would be the direction of PC2. So when we change the coordinate system in this reference frame, so here the dataset, in this case the dataset would not be correlated. So if this is my xy and there is no correlation between the dataset, then it would just appear like this, that for any value of x, y is not at all correlated with x. So after this transformation, along PC1 and PC2, there would be no correlation between the data. So yeah, we'll look at the steps of this transformation now. So first, we have to compute the covariance matrix. Then we compute the eigenvalues and eigenvectors of this covariance matrix. And lastly, we estimate the factor loadings. So factor loading is it gives us an idea of how much a principal component is related to a band. So that will help us in deciding which band is which band should be given more weightage during the analysis. Yeah, so here after calculating the eigenvalues and eigenvectors, the principal components would be the eigenvectors corresponding to these eigenvalues. And the principal component corresponding to the highest eigenvalue would be PC1. and total variance of that principal component would be given as eigenvalue divided by sum of all the eigenvalues into 100. So we'll do a problem on this, and I think then it will be more clear. So you can try this for some time. So here first we need to calculate the covariance matrix. Then calculate eigenvalues. Then eigenvectors. So yeah, only up to eigenvectors, then we'll be able to find the direction of principal component. So this is my band. So suppose this is band 1, band 2, and this is my pixels. Suppose. So we have to apply the same statistics that we saw on this data set. So for the calculation of covariance matrix, what we need is, so we saw that this is the formula for covariance. So first we need to calculate the mean, and then we need to subtract the mean from these original values, and then we can calculate the covariance. And we can use this formula to calculate the covariance matrix. So first we have to calculate the mean of each band. And now I'll subtract this mu1 from each element of band 1 and subtract mu2 from each element of band 2. So this would be 2 minus 4.5. And mu2 from each element of band 2. So now I'll calculate the covariance matrix. Is 1 by n C transpose C. So this is my C matrix, and n is the number of elements in this column. So uh, here n is equal to 6. So here we'll do the matrix multiplication. So the dimensions here are 2 cross 6, and here is 6 cross 2. So our covariance matrix will have the dimensions of 2 cross 2. So this is so you can cross check this with me. So this is the covariance matrix. So this is our first step to calculate the covariance matrix. Now we need to find the eigenvalues and their corresponding eigenvectors. So if we call this matrix as M, then to find the eigenvectors, we need to do M. We need to calculate the determinant of M minus lambda I, and then equate it to 0. Then we'll get a quadratic equation which we solve to get the roots of this equation. So I is an identity matrix. So lambda I would be, so here we have, sorry, this is 5.67. So here we get a quadratic equation in terms of lambda. So these are the two eigenvalues. So the eigenvector corresponding to this eigenvalue would be the first principal component. So we can find out how much variance it would cover. So would be so this component itself would cover approximately 95% of the data. So now we'll calculate the eigenvector corresponding to this eigenvalue. So we'll solve both sides. We have 2.92 x1 plus 3.67 times x2 to 8.22 x1. Yeah. So we will equate here and we get so if we find the ratio of x1 and x2 in uh, both these equations, this ratio is same. So So we have so this is the ratio between x1 and x2 from both the equations. So we have x1 is equal to 0.69 times x2. So here after the transformation, so this is suppose my band 1 and this is band 2. So this equation, if we plot, it will pass through the origin and we have 0.69 times x2. So this would be the direction of my first principal component. And if we calculate for the second one using lambda is equal to 0.38, then we can calculate the second eigenvector corresponding to that eigenvalue, and then we'll get the second direction which is along this axis. So here this direction of the principal component, it would cover the maximum variance in the data.
So the second eigenvector will be x2, right?
What?
Second eigenvector. The first one is x1 is equal x1. The second eigenvector would be x2. After calculating the
No. So eigenvector is this. It has both x1 and x2 components.
okay. So
So
it's lambda.
this is the relation. Yeah. Along this direction, that vector would be there.
So it's always perpendicular. Eigenvector 1 and 2.
Yeah. The eigenvectors would be perpendicular to each other. So we can. So if we take lambda is equal to 0.38, mx is equal to lambda x. Is equal to 0.38. Then similarly, you can calculate the eigenvector corresponding to this eigenvalue. Okay, so this was the problem on principal component analysis. I hope it was clear. Okay, now let's talk about band arithmetics.
It would be PC2, right? The next, once we get the result.
Yeah.
Just to make myself more understanding, see, in the PC1, right? So the DN values change accordingly as per this graph, and when it comes to PC2, it changes again the DN values, right? Is it the same way?
Yeah. So after transformation, so we have to find this first eigenvector, we have to find second eigenvector. Then there would be then we would have this matrix containing the two eigenvectors. So so this is our matrix containing both the eigenvectors. Then we'll multiply it with our original data, and then we will have the transform data into the new coordinate system. So like what we did here. Here, here. So what we have calculated is this.
Okay.
So we'll
Yeah,
multiply.
now this is for eigenvector, right? Okay, transform data. Okay, so this one, right? 3 into 1. It should be 1 into 3.
No, this was in this example the dimensions were different. So here we had 4 bands. In this example, we have only 2 bands. So that's why the dimensions are different.
3, 1. It's okay. So one column matrix.
So here we had 4, right? So for the other example, it would be a 2 cross 1.
Right. So the resultant should be one image with both the like PC2 and PC1, right? Or different image for PC1 and different image for PC2.
No, we will have 2 different images. So like how we saw here. This was the image after transformation using PC1, and then this was the image after transformation using PC2.
So why we are doing PC1 and 2 times? Is it something like every time for principal component analysis we should do 2 times?
No.
As we are getting.
Okay. Okay. So suppose we have n number of bands. So if we are talking about Landsat, we have like 11 bands. But then this is not very feasible. So we do the dimensionality reduction, and then we calculate different principal components. So we can calculate any number of principal components up to 11. So it
Okay,
is up to us how many components we choose. So first component will show the highest variance. Then this will have the second highest variance, this will have the third highest, and so on. So we can stop at a smaller value of principal components also if it covers enough variance in the data. So if suppose first four principal components, they only cover 99% or so variance, then we can only choose first 4 principal components and leave the rest.
No, I got the PCA how it does because if let us suppose out of 5 features, if you have removed one feature, that would be the first principal component analysis, and even after we are not good enough for the resultant, right? We'll go for second iteration. That I understand. Is it?
No. So it's only one time. So one time we calculate, first we have the covariance matrix. Then we calculate eigenvalues and eigenvectors from that. So we will have those many number of eigenvalues and eigenvectors. Then based on the eigenvalues, we can find out that each principal component has how much percentage of variance. And then based on that, we can select those many number of principal components.
Okay, see here in our case, right, for this problem, we got two eigenvectors. So that's the reason we got two PC1 and PC2.
Right.
So if we go for PC like a 4 or 5, so does the eigenvector should be also 5?
Okay, I'll explain. So here we had only 2 bands.
Okay.
Right. So for 2 bands, maximum number of principal components that we can get is 2.
Okay.
if we had more number of bands, so like in this case there were 4.
Okay. So n number of bands will be equal to n number of eigenvectors, and
Yeah,
those many principal components.
right. But then we need not take all the principal components. So we can choose to take less number of principal components, which show the higher variation in the data.
Okay. So if we are happy with the first two component analysis, then we can stop there. That's what you mean.
Yeah. So here I wanted to go from 4 to 3. That's why here I have only 3, and here I have 4. So I am trying to transform from 4 to 3. But then I can go from 4 to 4 also. So here then my dimensions would be 4 cross 4 for this transformation. Or I can choose to have only 2 transformed images. In that case, this will be 2 cross 4.
Okay. Yeah.
So yeah. So now let's talk about the band arithmetic. So here we perform operations on individual pixels like this to enhance or suppress certain features in the image. So we can have different operations like band addition, band subtraction, band multiplication, or band ratio. So here this is per pixel wise. So this is my output value, and for band addition the expression would be like this. So for subtraction, and so on. So we'll look at one application of this band arithmetic. So uh, this is an example of change detection using image differencing. So these are two different images. So first image, it was taken on May 3rd, 2000. This image was taken on April 19th, 2003. So these are the two images from two different time periods. And here we can clearly see that there has been a change throughout this time. So the water in this area, the water has changed to barren land, and here also there has been some change, and here also we see that there is some change, right? So um, after image differencing, so we subtract these two images to see how this land cover has changed over the time. So this is the difference image of these two areas, and this shows the histogram distribution of this difference image. So where the histogram is distributed around the mean, here these are the pixels which represent no or very less change. So like this pixel, suppose, so this pixel previously it was representing a water pixel itself, and uh, on the other end also it's representing the same pixel. So here when we do the image differencing, the value of this pixel would be around 0, or if we pick pixels over here, or uh, these are the vegetation pixels. If we pick these, then here also they are representing the similar area. So all these pixels, their value would not change as much. So all these pixels would be centered around the around 0. Um, However, where there has been a change, so like this area, or it's not very clear in this image, but here we can see that all these red dots. So here there has been a land cover change. So for these pixels, the change in value would be higher. So it would uh, the values of these pixels would be away from the center. So here we make a user specified threshold that after this threshold, uh, any values of the difference mask would be shown in green, and below this threshold, any values which are there, they would be shown in red. So this is the difference mask. So here we see that uh, this green portion, it shows the land where water pixels were present first, but now the water has receded, and this is shown with barren land. So before, when there were water pixels, the value of pixels would be less, so it would be a darker pixel. So suppose it was around 10 in an 8-bit image, and when this pixel is replaced with land, then now it is appearing brighter, so it would have a higher value. So suppose the changed pixel had around 200. So this difference, there would be a positive difference. So any pixels which have changed from water to land, they would appear on this side of the histogram. And this change in red, these are the pixels where barren land has been replaced by vegetation. So here they are appearing darker. So this is one application of change detection using band arithmetic. So yeah, let's do one problem on band arithmetic. You can try this for a while. So this is my band 1, this is band 2. So for band addition, um, we will so these corresponding pixels would be added. So we have 10, 200. Now, since we do not have minus negative values in an 8-bit image, uh, this will be saved as 800. Okay. For band ratioing, uh, we'll have to take ratio of elements from band 1 and band 2, right? So when we are dividing by elements of band 2, here there is 0. So we cannot divide by 0. So to reduce this error, we add a constant to both numerator and denominator so that there wouldn't be a change in the image as such, but then this dividing by 0 problem wouldn't be there. Okay, so let's talk about image classification. So as explained in the lecture, uh, there are two learning techniques. I mean, there are two ways to do image classification. First is learning techniques. These learning techniques are further classified into uh, unsupervised and supervised learning. So examples of unsupervised learning are k-means clustering or isodata clustering. and all the other classifiers which were explained in the lectures. So let's so this was pretty clear from the lecture. So we'll just go through it very quickly. So yeah. So in case of supervised learning, we have a well labeled set of training data. So, for example, here we need we need to classify different kinds of fruits in this bucket. So, first, in supervised learning, uh, we will provide a used dataset of training samples where um, it would so the machine would be taught to identify different kinds of fruits based on their shape or color or texture. So the machine would be given a set of training data sets. So for apples, it would be told that uh, any object which appears red or it appears round has a small um, so it has this shape, or for banana it would have an elongated shape, it appears yellow. So based on different characteristics of the training dataset, the model it would learn to identify different objects, and then it would classify based on its training dataset. Whereas in case of yeah in case of unsupervised learning, there would be no training dataset as such. So, and there would be no prior information. So, for this algorithm, suppose this is an image based on this is an image of cats and dogs, and the machine has no idea about how the features of these animals are. But then, using the current data, the machine would, based on different features of these animals, it would classify this data set. So, here, if we are talking about the remote sensing data, then it would form different clusters of data based on their similar characteristics. So here the cats would be categorized into one cluster based on their different features like eyes or ears and other features, and dogs they would be categorized into a different cluster. So based on this there would be different clusters uh, depending on similarities in their features. So this is an example of unsupervised learning. So if we were to talk about differences between unsupervised and supervised learning, here we have unknown number of classes. Here the number of classes would be provided by the user itself. Here we would have no prior knowledge about the data or how the classes are going to be. Here, the classification is based on a training data set. Here the classes would be based on spectral properties. Yeah, so there are some drawbacks to both the techniques. So here the derived clusters might be unidentifiable. Mm. Okay. So let's talk about the accuracy assessment. So both the classification systems, supervised or unsupervised, what they are trying to do is, if I have a data set containing n number of pixels, so based on the property or characteristics of each pixel, uh, they are being classified into different classes. So for remote sensing data, we might have different classes like water or vegetation or soil and so on. So based on these pixel values, we are calculating what class uh, the pixel would belong to. So then there are different types of classification techniques which were explained in the lectures. So to check whether actually the classified pixel belongs to that category itself, we need to do accuracy assessment of that classification technique. So suppose my classification algorithm has classified this pixel as water, but then the pixel, when I go to the field and check the real data at that coordinate, I find that this pixel corresponds to vegetation. Then it's a wrong classification. So accordingly, we need to check if the classification accuracy of that technique is how good is the accuracy to be uh, to be able to decide whether to use that classification technique or not. So for accuracy assessment, we have test dataset which is collected from ground-based measurements, and then we use different techniques to calculate the accuracy of our classification. So one of the important parameter is the confusion matrix. So in a confusion matrix, we have this is the ground truth data, and this is the classified data which is present in the rows. The ground truth data is present in the columns. And suppose I'm classifying my data into 4 different classes. So here is my class 1, class 2, class 3, class 4. Now here I will have the statistics of the data. So this is my ground truth data. So in ground also, uh, this uh, pixel would show the number of pixels which are classified as class 1 in ground also and class 1 by our classification scheme also. So this is x11. This x21, this shows the number of pixels which are actually class 1 on ground, but then in the classification they are classified as class 2. Similarly, this is class 1 on the ground, but then classification it has been classified as class 3 and so on. So here we have x12. So this is the confusion matrix. So here I will have total number of pixels on the ground which are class 1. So this is total number of pixels which are class 2, total number of pixels which are class 3, and total number of pixels which are class 4. And this would be total number of pixels which are classified as class 1. So this is the notation. And then here we would have total number of all the pixels. So there are different accuracy measures which can be derived from this confusion matrix. So we have accuracy measures. So first is naive measures. So this includes the overall accuracy, per class accuracy. So here we have users and producers accuracy. Second, we have the kappa coefficient. And there is tau coefficient and so on. So yeah, for naive measures, overall accuracy is given by total number of correctly classified pixels divided by total pixels. Then we have per class accuracy. So we have producer's accuracy and user's accuracy. So producer's accuracy will be here. So it will be given for every class. So for class 1, my producer's accuracy would be total number of pixels which are rightly classified as class 1 and total number of pixels which are actually class 1 in my reference data. So it will be x11 divided by x plus 1. So this value. So this is the total of all. This is the sum of this column. Then similarly for my class 2, it will be x21 divided by x plus 2 and so on. And similarly for user's accuracy, it will be total number of pixels which are rightly classified as class 1 divided by total number of pixels which are classified into class 1. So it will be x11 by x1 plus, or x21 by x22 by x2 plus, and so on. And a definition of kappa coefficient. So this was explained in the lecture also. So kappa coefficient is n cross A minus B divided by n square minus P. So where n is total number of pixels, A is total number of correctly classified pixels, and B is the sum of product of these values. So product of this and this, this and this, this and this, and this. So we'll do a numerical on this, and then it will be more clear. So try to calculate the overall accuracy, user's accuracy, and producer's accuracy for this given table, and also compute the kappa coefficient. So this would be the last problem for today.
Really, like, it would be great if you also just detail on the indices. I think we have missed the indices.
Uh, you mean NDVI and NDWI?
Yes, yes, right.
Okay, so I think the time for today's session is over. So we'll discuss it in the next session.
Okay, but this one, right? So I think there are, as per the problems, right? There are where I can find two other types of indices in the options. But whereas in the lecture, right, it was only two to three, like NDVI and then NDSI was explained. So is that something like in the further sessions we'll have those indices concept again?
So it was the part of digital image processing. So I don't
Okay,
know.
okay,
It won't be there in the next lectures, I think. But
okay.
I'll try to cover it in the next session. In
Sure,
brief.
sure.
Okay.
Okay.
All right. So here I'll quickly explain this. So here the producer's accuracy for class A. Okay. So let's look at the overall accuracy. It would be, so total number of pixels which are rightly classified are 35 plus 11 plus 38 plus 2. So overall accuracy is 86 by, and total number of pixels is this. So my overall accuracy is 52.76%. For producer's accuracy here, this is total number of pixels which are A is 53. So for class A, my producer's accuracy will be 35 by 53. For here it will be 11 by 39, 8 by 64, 2 by 7. And here we'll have 35 by 61, 11 by 18. Okay. And for the kappa coefficient, we'll have 163 into 86 is the uh, total number of pixels which are rightly classified, minus we have B. So B would be 61 into 53 plus 39 into 18 plus 64 into 63 plus 7 into 21. And in the denominator we have 163 square minus B. So B is equal to, I'm getting 8114. So the value of this kappa coefficient is 0.3199. Okay, so we'll try to talk about the indices in the next lecture. And that's all for today.
Yeah, thank you.